Hi geometry students, this is Mr. Fugay, and this video is going to talk about the Pythagorean theorem. Now, as you're sitting here to watch this, more than likely you've probably already heard of the Pythagorean theorem. So this video is going to serve more of a review, a refresher, and maybe a little extension into how we're going to apply it in this course. So let's first talk about what it exactly is. So the Pythagorean theorem tells us a relationship about how the side lengths of a right triangle are related to each other. So traditionally, we have two legs, and those legs are usually labeled as A and B. They don't have to be. Sometimes X, Y, and Z are used, or X, Y, and R, but in most cases, A and B are called our legs. The order of these, when you write them out, does not matter. Now, there is something important to note because we just talked about isosceles triangles and how the legs of an isosceles triangle are equal to each other. When we talk about the legs of a right triangle, they do not have to be equal to each other, unlike the legs of an isosceles triangle. So I know this is a little vocabulary confusion, that legs are used to both refer to the non-hypotenuse of a right triangle and simultaneously used to describe the equal sides of an isosceles. But I'm letting you know that now here in this video so that you are aware that they can mean two different things depending on whether we're talking about a right triangle or an isosceles triangle. Now that last side C, we call that the hypotenuse. And that hypotenuse is always located opposite from the right angle. Now, based on our lesson from the last unit where we were ordering sides and angles, the reason why this is true is because the right angle is the largest angle of a right triangle. And so if we know it's the largest angle, we know that the largest side must be opposite or furthest away from it. So I want you to utilize that when setting these problems up. And we will typically label this as a C. So here's your first chance to look at this. I want you to, in these diagrams, to label A, B, and C in each of these right triangles. Go ahead and pause this so that you can try that out yourself before I reveal what the answers are. All right, hopefully you have paused. The right angle opposite side is going to be C. So that's a non-negotiable in both of these diagrams. You look at where the right angle is, the side that is furthest away from it is going to be our hypotenuse. Now, where you decide to put A and B is up to you. If you call this A and call this B, or maybe you reverse it and say this is B and this is A, it doesn't matter, as long as you recognize that these are considered your legs. So A and B, or again, you could do it vice versa. Now, when you first learned the Pythagorean theorem, hopefully you had the opportunity to learn why it works. But I wanted to give you another opportunity in case you were not sure why a squared plus b squared equals c squared works. I want you to take a look at this video right here. So this should be a hyperlink that you have access to that will take you to a video also on YouTube. And I will also post this link down in the description of this video. So feel free to pause the video right now to check it out because it provides a visual that shows that A and A create A squared, B and B create B squared, and then when they turn this figure around, all of the liquid that's inside of the A squared and the B squared filters in to this third side here, which is C squared. It's a really helpful visual to help you understand why this relationship exists from an area of a square perspective, which is a little bit different than maybe what you might have remembered, but this video will do a good job serving as that. So moving forward from that, let's talk about how we use the Pythagorean theorem. So the idea here is once you identify what is considered your hypotenuse, we can set up our Pythagorean theorem as simple as doing a squared, 24 squared, plus 45 squared. Remember, those can be interchanged, equals. So I could do question mark squared, but let's just use a letter. We'll use X instead for that. So what we will do now is take that 24 squared, add it to our 45 squared, and we get this really large 2601 equals X squared. The last step of this is we will take the square root of both sides. And when I do that, when I take the square root of 2601, we actually get a nice even 51 as our missing side, and that is our answer. Now, you might notice, for those of you who took Algebra 2, that when you take the square root of an equation, you are technically supposed to write plus or minus 51. The reason that I am omitting that and not speaking about that here is we are talking about a length. And since x is a length, we're not going to have a negative value for it. So that's why we're leaving it as positive. Now I want you to try this next one. Pause the video and see if you can try to solve this one. All right, looks like hopefully you've had a chance to try this out. Take a look at the work here. So the only thing that's a little bit different is at this step, and I didn't show it, but in this case, because the hypotenuse was known, we had to make one of my legs the variable. And in this case, we had to subtract the 1296 from both sides. So when you subtract it from both sides, you get 5929. You take the square root and you get 77. Now it just worked out really nice that for these first two examples that I did, that we got whole number answers. So we do need to discuss this last idea. What if there is a radical? So I wanted to show this final example. So the hypotenuse here is our unknown. So we're going to go ahead and set up another Pythagorean theorem. So when I set it up, it's going to be leg squared, 8 squared, plus, now the other leg is 2 root 2. My recommendation is to wrap that in a parenthesis, because we're going to talk about how to square that in just a moment. And that equals c squared. Now, when I do 8 squared, yeah, we get 64. When you do 2 root 2 squared, if you use a calculator, and as long as you put it in parentheses, it will square the number correctly. But just to show you on the side here how this actually works, is if you are squaring 2 root 2, let me undo that. Oops. There we go. If you square 2 root 2, it's the same thing as taking 2 root 2 times another 2 root 2. You're going to multiply the 2's together to get 4. You're going to multiply the root 2's together to get root 4. So that's really 4 times 2, or just 8. I know I wrote that out a lot more than probably what a lot of you need to do or need to see, but I wanted to emphasize what it actually is happening. You're squaring both the 2 and the root 2, and then multiplying their results together. So in this case, that's going to be an 8. And so from here now, we're just going to do 64 plus 8, which gives me 72. When you take the square root this time, if you put this in your calculator as square root 72, you get 8.48528, blah, blah, blah. What I want to try to do here is to try to write this in radical form, simple radical form. So you can use, if you have the TI-30 calculators, it has the ability to simplify this for you. But it's also helpful to know how to do it yourself. So what I usually do for this is I'll create a quick factor tree. Know that 72 is 9 times 8. 9 is 3 times 3. This represents to me a perfect square. And so that perfect square can be essentially pulled out of the radical. 3 times 3 is 9. The square root of 9 is 3. So this becomes 3. And then the 8 also breaks down as 4 times 2. And 4 is 2 times 2. So I can also pull a 2 out of this as well. That makes it 6, by the way. And then the only number that we were not able to pair off as a perfect square was a 2. So that remains on the inside. And just as I mentioned, since I have a 2 and a 3 here on the outside, I can just multiply that together to say 6. So the precise answer here in radical form is 6 root 2. Now, if you enter 6 root 2 in your calculator, you should also get 8.48528, blah, blah, blah. But we want to try to get in the habit of writing these in radical form, as they will serve us a greater purpose later on in the course. So that concludes this review of Pythagorean theorem. And so to wrap this up, there are 3 examples down here I would like you to try. And the challenge for you is to find these missing lengths and write your answers in both decimal form as well as radical form. Best of luck on that work, and I hope you have a good rest of your day.